new things that they keep hearing about in, say, newspapers, or they see on some TV shows, and they don't get a chance to interact with experts in the field to satisfy their curiosity. And this is a small effort from our part to help you with that. The LNMIIT, it actually is a deemed university, and it was established in 2002. And in a short span of time, it has made some name for itself. And the department here is actually actively involved in doing some research work and in teaching, and we offer a couple of programs here. So we offer MSc in physics, and we also offer PhD, provide PhD opportunities for motivated students. And with these few words about the Colloquium series and about LNMIIT, let me introduce today's speaker, Professor Gautam Mandal. So I'm actually especially pleased that Professor Gautam Mandal is today's speaker. He is currently Raja Ramana Chair Professor in International Center for Theoretical Studies, which is a part of the Tata Institute of Fundamental Research. Before joining ICTS, Professor Mandal was in the theoretical physics faculty of TIFR for over 3 decades. And he also had various visiting professors in various international institutes, like the Institute for Advanced Study in Princeton. Also, he was visiting professor at CERN in Perimeter, Canada, and in KEK, Japan. He's also a fellow of the Indian National Science Academy and the Indian Academy of Sciences. Professor Gautam Mandal obtained his PhD from TIFR Mumbai, and he is well known worldwide for his work on string theory and quantum field theories, and also in more recently he has been working in statistical physics towards the the focus of his work has always been on string theory, and even in string theory, it has been some of his well-known work includes understanding black hole solutions in string theory. In fact, he was one of the first persons to discover black hole solutions in string theory, and he was also one of the first persons to provide a proof that black hole evaporation does not violate quantum physics, which is essentially related to what he's going to talk about today. So without much ado, let me invite Professor Mandal to present the colloquium on the arrow of time and the black hole mystery. Professor Mandal.
Thank you, Rakesh. Can you all hear me and see the slides?
Yeah, we can hear, but I think there is a suggestion that if you can switch off your camera, probably the visibility of the slide will improve. So can you switch off your camera only?
Okay, I'll do that.
In the meantime, I'll make one more announcement that students who have any questions during the presentation, you can on the top menu bar, you will see a hand symbol which says raise your hand. Okay, so you can, whenever you have any question, you can raise your hand and we'll try to unmute you. And once we unmute you, you will have to unmute your mic from your end, and then you can ask your question. Otherwise, if you don't want to ask the question orally, you can also type your question in the chat box, and we'll try to take up that question with Professor Mandal. And otherwise, of course, at the end of the presentation, we can also take more questions.
Okay. Is the slide better now?
Yeah, slight better. So you can start now.
I'm hearing a lot of echo. I don't know what to do about that. There's a lot of echo. But
So
anyway,
people need to turn off their mics, I think. All the organizers, except for Professor Mandal, please
yeah,
turn off
hello.
your mic.
Yeah, anyway, let me go ahead and talk. Yeah, shall I start?
Yeah.
Okay, so thank you, Rakesh, for the kind introduction. And thank you for the opportunity to present this talk. So this is a semi-technical talk on the subject of the arrow of time and the black hole mystery. So let me explain what this mystery is about. So one of the outstanding mysteries of science is the arrow of time. What is this mystery? Let's consider two examples. One is from daily life, namely that it's a well-known phenomenon that hot tea gets cold, but never the other way around, that cold tea gets hot by itself. This is called the thermodynamic arrow of time because it has to do with the second law of thermodynamics, as I will explain. The second example would be from the physics of black holes. Objects can enter a black hole but not come out. So that's another arrow of time. So I'll explain about black holes, in detail later on. This is a cartoon of a black hole in which the central object here, this black spot, is a black hole, which can absorb things but not emit. So that's the arrow of time. So let me explain. By an arrow of time, we mean that if we could reverse time, then we would see a seemingly impossible phenomenon. So we consider an event and we consider the time reversed event, and the time reversed event would seem impossible. If that happens, then we say that there is an arrow of time. For example, cold tea getting hot by itself never happens, or at least apparently never happens. So that's an arrow of time. What's the mystery here? This is a common phenomenon. The mystery is that the fundamental laws of physics tell us that the time reversed version of any event is possible. So cold tea getting hot is actually possible. Okay. Now the question is, if they're actually possible, why don't they happen? Is there something still missing in our understanding of the basic laws of physics which encode an arrow of time, but we simply don't know it? Before we go to more details, let me give you a few more examples of the arrow of time. So example number 3 is cosmological arrow of time. So this has to do with the fact that we have an expanding universe. 14 billion years ago, approximately, the universe started from an event called the Big Bang, and it's expanding ever since. Okay, so this is clearly a time irreversible phenomenon and an arrow of time. And perhaps the most mysterious of all is the arrow of life. So it's the beginning of life from inanimate matter to living things and the subsequent evolution. So this is a picture here of a famous experiment of Miller and Urey, who tried to do some experiment with inanimate matter and create life. That didn't work, but in practice it did happen, that life did evolve from inanimate matter. And first very simple organisms came, and then of course evolution gave rise to higher and higher more and more sophisticated life forms. So today we're going to talk about mainly the first two arrows of time, namely the thermodynamic arrow of time and the black hole arrow of time. So let us do an experiment. So let us take 2 glasses of water, one a cold glass of water and the glass of hot water. Okay, and here I start the experiment. I drop some drop of ink in both the glasses of water and see what happens. What happens is that the ink, of course, spreads into the water. This is, of course, an everyday phenomenon. Let us watch this video backward. Okay, so now I start the video backward. So the spread out ink, it sort of goes and collects into the tip of the pen. This, of course, is an impossible phenomenon, but as we will explain, it looks impossible. As we will explain, this impossibility is actually a surprise. To understand why this is surprising, let's zoom in. Let's see this ink spreading under a very powerful microscope. What we will see is something like this. This is a picture of an actual electron microscope under which the molecules of the medium can be actually seen. So if we watch them in real time, then what happens is that these molecules, they all collide and they spread into the beaker. And at this stage, even if you look at the individual molecules colliding, you cannot make a distinction between a video being played forward or played in the reverse. In other words, under a microscope, there is no arrow of time. How does it appear in the macroscopic world? So that is the issue. Let's understand in some detail the time reversal symmetry of the microscopic world. Take a video of two colliding particles like this. If this is the actual event, then this is the time reverse event. But the time reverse event is also allowed by the laws of physics equally well. Why does that happen? The time reversal symmetry follows from a very simple mathematics of the fundamental laws of physics. Namely, take Galileo's law, the law of inertia, which says that in the absence of a force, velocity does not change. In other words, dx dt is constant. You can rewrite that as the derivative of a time derivative of the time derivative of position is equal to 0. So there are two times here in this equation. As a result, if you take t going to minus t, the equation does not change. The same thing happens with Newton's laws, which says what happens if there is a force. So in the presence of a force, velocity changes like this. The acceleration is given by force divided by mass. In the expression for the acceleration, once again, time appears twice. So therefore, if t goes to minus t, the two minus signs cancel and then there is no change. It is precisely this that says that there is no distinction in the microscopic world between the past and the future, which is t going to minus t. Time reversal symmetry also works in quantum theory. So there's a bit of mathematics here, which you may ignore if you are not familiar with this. This equation is called the Schrödinger equation. And it says basically that if you start from some state, quantum state of a system given by something called a wave function, then if you go forward in time, then from the wave function psi naught, you reach psi 1. But if you start from psi 1 and go backward in time, you reach psi naught. Okay. So things, if some process can happen in the forward direction, it can also happen in the backward direction. Okay, so that's the time reversal symmetry of the basic equations of theory. But if you don't like these equations, you certainly know that if I take an atom and take a photon, a particle of light, then an atom can absorb light. That's the reason why we feel hot in the sun. An atom can also radiate light. That is how light bulb works. So the forward event and the backward event both can happen. So the question again is that if there is no arrow of time on the fundamental microscopic level, how do the arrows of time appear? Let us go back to our experiment with the ink and look at it a little bit more simply. Let us divide the beaker into two chambers. Let us call them head and tail. We'll keep track of only the head-tail property of each molecule. So, in other words, if I want to characterize a molecule, I just want to figure out whether it is in the left chamber or in the right chamber, which I have called head or tail. So we'll keep track of only that property. When the ink is released, the molecules are all in the head compartment. After the release, the molecules scatter into both compartments by their random collision. So after a number of collisions, there are equal number of molecules in the compartments head and tail, like this. And they never seem to go back to the all heads configuration. This shows the arrow of time. How do we resolve this conflict of the arrow versus no arrow? One possibility is that the fundamental laws of physics were actually not quite correct. There is possibly a secret time asymmetry in fundamental physics, which leads to this arrow of time. Now, this has been checked, to amazing precision, to many orders of magnitude in the underground experiments of the LHC at CERN, then cosmic experiments, and in experiments in our solar system, and so on and so forth. And the conclusion is that no, there is no arrow in the fundamental laws. There are some tiny possible violations of symmetry, but they cannot explain the kind of macroscopic violations that we are thinking of. So how does one understand? So I hope that you understand that there is a problem here, that under the microscope there is no arrow, but macroscopically there seems to be an arrow of time. So let us repeat our experiment now with coins instead of molecules. So our model will be that, okay, so let me explain with some figures. So suppose we begin with 10 coins, all with heads up. We now shake them in a box and toss them on the table. The following are the results of a real experiment. You can do this experiment on your own. So I start with 10 coins with all heads up. So 10 heads here. Then it goes to 6 heads and 4 tails, and then 3 heads and 7 tails, and so on and so forth. So every time you shake them in a box and then toss them on the table. Okay. So these are the configurations which I actually got in an experiment. Is there a pattern of these coin sequences? Here the coins model the molecules, and the shaking of the coins models the molecular collisions. Okay. So this is a simplification that we are doing to understand the basic dynamics in the hope of understanding the arrow of time. So once again, the modeling is the following. 10 heads, our initial configuration here, is like all molecules in the left chamber, and something like 5 heads and 5 tails would be equal numbers in both chambers. We want to see whether there is a time irreversible flow from the first kind of configuration.
Well, just a minute, Gautam, there seems to be a question. So
yeah,
someone has raised his hand.
Yeah. Please go ahead.
Yeah, just a minute. Rahul, can you unmute your mic and ask the question? Rahul, you need to unmute your mic and then ask the question. Otherwise,
Hello.
you can, yeah. Please go
Hello,
ahead.
sir. Actually, I don't have a question, but the presentation is not very clear. Like everything is very blurry. So, is it possible if the speaker can send the slides to someone with a better internet connection, and then the other person can change it for the speaker?
Rakesh, we can try that.
Yeah, we can try that. So maybe you can handle
But
the slide because I'll be
the
handling.
problem is that it's a PowerPoint presentation in which the animation is controlled by me. So is it very, very blurry? I mean, I switched off my camera though.
But it didn't improve much. So it's basically an internet issue. Because we can hear you clearly, but we can't see the slide properly.
I see. But it doesn't happen on Zoom somehow.
Yeah. Probably the number of participants is more, and I do not know what is the reason, but somehow we can't see that slide because we can continue, but the thing is that it is not clear.
Okay, maybe I'll change my position a little bit. That works. Did that make any difference?
Not really, I think.
So what shall I do? Will I continue?
I mean, the slides are blurry, but I mean, it's momentarily, and then we are able to see. I don't know about the participants. For us, it's, I mean, it's not that bad in the sense it gets blurry for a few moments, for a few seconds, and then it improves, and then it becomes blurry again. So
It's same here also. I am also in a different network and I can see it, but for momentarily it got blurry. So I think it would be very difficult if somebody else because use the slide and he want to speak from there. It would be even difficult for us to manage. So you can continue. I think you can continue.
Yeah. Okay. All right. So
okay, so just a minute. There seems to be a question actually this time. So Siva, you can ask your question. Please unmute your mic and ask your question.
Good evening, sir.
yeah. Hi.
I just want to ask a question that you said, like you showed that like the acceleration thing, the time reversibility is there, and also in quantum mechanics there is time reversibility. But my question is that is there any sort of relevant length scale up to which this time reversibility holds true?
Sorry, could you repeat the last part of your question?
Is there any kind of relevant length scale? Because like whatever you showed, the Newton's law and all, they all apply to like classical mechanics, like to big things. And the quantum mechanics thing, there is also the time reversibility. You showed that. Is there any kind of relevant length scale?
Is there any kind of different length scale beyond which the arrow of time appears? Is that your question?
Yes. Yes.
Okay, so that's a very good question. So we will find that it actually has to do with the system size indeed, but in what particular way is coming in a few slides. That's a very good question. So I will address your question. So just wait for two more slides, three more slides. Okay, so here we are, so in which we are modeling the spreading of the ink by the coin tossing experiment. And so as I said, I begin with 10 heads, which model all molecules in the left chamber, and 5 heads, 5 tails, which is like equal number of molecules in both chambers. So So now we go back to this sequence of coin configurations, which will in fact contain a wealth of information. Okay, these numbers like 10, 10H going to 6H40, 3H70. What information do they contain? So to do this, we need to do a slight bit of mathematics. That is the entropy of this coin configuration. So suppose you have n coins. So you are shaking n coins, putting them on the table. What is the probability of 8 heads? Okay. In a random trial, what is the probability of 8 heads? Now, the total number of possible head-tail configuration is omega, that is 2 to the power n. You can easily count this. It's like for every coin, okay, it is a possibility of head or tail. So that's 2 times 2 times 2 times 2, etc. That's 2 to the power n. That's the total number of configurations. The number of configurations with each heads is the same as in how many ways you can choose h out of n. So that's n choose h, which I have called omega h here. The corresponding probability of having h heads is given by the ratio omega h divided by omega. And the corresponding entropy is given by the Boltzmann constant times the log of configurations. Okay. So here's some example for n equal to 10 coins. So on the left column, I'm talking about configuration types. So all 10 heads, there is only one such configuration, that's 1. And 9 heads and 1 tail can come like, the tail at the absolute end, or it's somewhere in the middle, and so on and so forth. So there are 10 such configurations. And similarly with 8 heads, there are 45 and so on. And overall, there are 1024. That's 2 to the power 10 number of configurations. So here are the probabilities and here are the entropies. Now, I translate the sequence of coin configurations to a graph like this. Okay, so x-axis is time, and the blue curve here is the probability of time, and the red curve is the entropy as a function of time. Okay, so as I said, each of these coin configurations translates to some value of the entropy. So this is the entropy versus time curve. To begin with, I have 10 heads, which corresponds to entropy equal to 0. And at some point, I have 5 heads and 5 tails, like in here. Can people see my cursor? I'm not sure.
Yeah, we can see the movement of the cursor.
Okay, good.
By the way, there was another question in the chat. Gautam, there was a question in the chat. So I think it was with reference to this entropy curve. So somewhere the entropy curve goes down and then goes up again. And the question was, isn't this violation of the entropy law?
Very good. Very excellent question. So I'll address that in the next slide itself. So both questions that have been asked so far are very good questions. So the answer, in short, is that actually entropy can go down. But as we go to larger and larger systems, this going down business that becomes rarer and rarer. So let me explain that in more. Okay. So entropy seems to roughly increase in time, and as has been correctly observed, it is going down a little bit sometimes. The question is, does it stay up always? For example, does it ever go back to 10 heads configuration? So now you can keep doing these experiments, take 12 coins and do 8,000 tosses. This is difficult to do with hand, so I have done a computer experiment with this, and this is what I got. So x-axis time and y-axis entropy again. So this is how the entropy curve looks like. So as you can see, the entropy rises and stays high most of the time. Of course, it goes up and down, except at, okay, but it stays high. Okay, on an average, it stays high, except at long time intervals, like 2000 here you see, which is comparable to the total number of configurations here, which is 2 to the power 12, that's 4000 approximately. So at very long time interval, after 2000 tosses, let's say, which are called Poincare recurrence time, the entropy can actually come back to zero. That is to say, it comes back to the 10 heads configuration or 10 tails. Okay. So most of the time it remains in the probable configurations, but sometimes after a long time, exponentially large times, it can come back to the original configuration. Okay, so thus we see the emergence of an approximate arrow of time in which the entropy roughly increases and stays high for long times. But the arrow of time is only approximate, since if we wait long enough, the entropy will come down to zero again. How long is long enough? The Poincare recurrence time grows exponentially with the number of particles. This is a very rapid increase with n, exponential, which exceeds usual time scales of observation very soon. So you don't see the Poincare recurrence at all. For instance, for a room full of molecules, say with total number which is of the order of the Avogadro number, 10 to the power 23, the Poincare recurrence time is roughly proportional to 10 to the power n, which is like 10 to the power 10 to the power 23. Multiplying by the typical time scale of collision, we find that the Poincare recurrence time is much, much bigger than the lifetime of the universe. So clearly, you have Poincare recurrences. Hence, we understand how the time arrow of the second law of thermodynamics emerges and how it is not in conflict with time reversibility of basic microscopic laws. So, in other words, it does go back, but it takes such a long time that we don't see it. Okay, so that is but in answer to the second question that was asked, it is indeed true that the entropy does not strictly monotonically increase. Okay, the strict monotonic increase becomes better and better with larger and larger systems, but it always has a fluctuation around the maximum entropy configuration. Okay, so it can go down a little, go up a little bit, and so on and so forth. But on an average, this entropy increase law, it does follow. Now, so have we therefore settled the issue of the thermodynamic arrow of time? Not completely, because of the following. For some macroscopic systems, the coin analogy is good, while for some others it is not. The former systems are called ergodic, where after some short interaction span, which you can compare with coin shaking, the previous state is forgotten, essentially. Okay? But there is a second class of interacting systems, for example, the solar system, which does not behave like the shaking coin. It remembers how it behaves today and comes back to it after a certain period. It never goes to a configuration in which the planets, the asteroids, the comets are in random, disordered arrangement, reaching some equilibrium, which is a complete mess of asteroid dust like below. Thankfully, it does not happen that way. Thus, some systems show order and periodization, while some others reach equilibrium and show an arrow of time. How do you know which is which? So this is, of course, a very important question and is under active research for the last 100 years, and the research is still going on in this one. Which systems behave like ordered period systems, and which systems show dissipation chaos? So there are, very profound works by Kolmogorov, Arnold, and Moser, these three gentlemen here, who have worked on periodic motion, periodic and ordered motion, and Boltzmann and Sinai and Lyapunov, who have worked on systems exhibiting dissipation and chaos. So thus, although the periodic class of systems do not show an arrow of time, and hence do not have a thermodynamic description, for both classes of systems, the periodic as well as the ones that show arrow of time, there is no conflict with the basic law of motion. either Newton's laws or Schrödinger's laws. So we have shown how atoms of time appear in the systems where they do. There is no conflict with the basic laws of motion. This therefore brings us to the second puzzle of today, namely the black hole. So let me say a few words about black hole. What are black holes? Suppose that a star is so heavy and dense that not even light can escape from it. We will then never be able to see such a star. Such a thing is called a black hole, which is an invisible object. It can cast a shadow, however, which we can detect. So there's some famous picture of black holes, which was taken a few years ago by something called the Event Horizon camera. Now, can a star be so heavy? So this is what we are saying, that if there is such a thing that even light cannot escape from it, then it would be invisible and it would be a black hole. Now the question is, can a star be really so heavy and dense that its escape velocity exceeds the speed of light? That's what we're saying, right? If light cannot come out, then its escape velocity is even more than the speed of light. So according to a Newtonian calculation, which is not the final calculation that we do in this regard, the escape velocity from a body of mass m is given by this formula, square root of 2gm divided by r. For this escape velocity to be bigger than the speed of light c, we must have this point. That is to say, this radius of the star, which appears in the denominator, okay, it should be small enough so that the escape velocity becomes big and bigger than the speed of light. So how small? So the radius of the star has to be less than what is called the horizon radius, which by this formula is given by 2gm by c square. This is the calculation due to Laplace, which amazingly actually agrees with the calculation that you do from Einstein's theory of gravity to find out that indeed there are objects like a black hole, which if they shrink below the horizon radius RH, then they even light cannot. So there are such. Okay, how do they actually appear in the astrophysical scenario? So you take a collapsing star in which it has finished all its fuel and so on. So it just has become some mass of particles and under only gravitational interaction. So it's collapsing therefore under its own gravity, and it keeps shrinking. And as we found in the previous slide, if it keeps shrinking beyond a certain stage, okay, it will become small enough so that it will become a black hole. So this was something that was predicted by Chandrasekhar in the lifetime of a black hole of a star which has finished all its fuel. And there was a theoretical model by Oppenheimer and Snyder where they actually showed by solving Einstein's equations that such a thing really does form. So now, if that happens, if black holes do form like that, then there is an arrow of time that because. So this is a cartoon picture of a binary star system in which this red thing is a black hole, and the white big star is a visible binary companion of the black hole. So clearly, things can go from the binary star into the black hole. That is allowed. Black holes can absorb, no problem with that. But the reverse process of that thing coming out of the black hole, of course, is not allowed because if even light cannot come out, nothing else can, because light is the fastest object. So Hawking in 1974 argued that there is a certain quantum refinement of the arrow of time. The arrow of time does remain, but there is a quantum refinement, which is what the black holes can absorb. They can also emit. However, what is emitted is not what goes in. It is thermal emission, typically very faint thermal emission of temperature of the order of 10 to the power minus 8 Kelvin for a solar mass black hole. And further, the emission probability is far less than the absorption probability. In the classical limit, the emission probability goes to 0, and that's the usual arrow of black holes. So therefore, even with the quantum refinement, there is an arrow of time. So this gave rise to the black hole paradox, which Hawking in 1974 enunciated as follows. Since quantum mechanics is time reversal symmetric and black holes are not, black holes violate quantum mechanics. So of course, before black holes were actually observed in the sky, it would always be black holes are some imaginary objects. They are never there. Therefore, quantum mechanics is safe. But black holes have been observed. So therefore, if we believe Hawking, quantum mechanics will be violated. Staying within the description of a black hole as a macroscopic object, as in Einstein's theory of gravity, it is impossible to resolve Hawking's paradox. So this was a great challenge to theoretical physics for decades. However, if we have a microscopic atomistic model of a black hole, then absorption of a photon by a black hole is simply the following. It sends the atoms of the black hole from a lower energy state to a higher energy state, which have higher entropy. The emission of a photon sends it from a higher energy state to a lower energy state, which has lower entropy. So this is what it is. This is the black hole, the lower state, the lower energy state, which I have described by a small degeneracy. Okay, so there are just in this cartoon, there are just 3 states at energy. So this is the lower, this is the lower energy state of the black hole, and after absorbing the photon, it goes into a higher energy state, which has in this cartoon 6 states with the same energy. So this is what happens as you go to higher and higher energies. The degeneracy of states at that energy increases. Okay. This is simply the increase of entropy. So the entropy of the higher energy state is more, and for a black hole or big system, much more of the higher excited state compared to higher energy state compared to the lower energy state. So as a result, if you do have an atomistic description, then the fact that the absorption probability is much higher than the emission probability is simply the fact that absorption takes you from a lower entropy state to a higher entropy state, and emission takes you from a higher entropy state to a lower entropy state. So as a result, since going to a higher entropy state has higher probability, so the absorption probability is much higher than the emission probability. Okay. So as soon as you have a microscopic atomistic model of a black hole, you can do this calculation and show that the black hole arrow of time is simply a consequence of the thermodynamic. So here is a picture of how the atomic model came about. So this is the model that came from string theory. This was a famous model of Strominger and Waffa, who showed the black hole can be modeled by a whole system of very tiny vibrating strings, which are bouncing about much like air molecules or like molecules of tea in the teacup. Hence, the black hole arrow of time can be identified with the arrow of time of thermodynamics. In particular, just like the arrow of time of thermodynamics, even the black hole arrow of time is actually approximate. Okay. So I have not given any reference in this talk, but if there are questions later on, I can give you the reference.
So there is one question.
Yeah.
which is that inside a black hole, if there is a singularity, does time exist?
Sorry, say it again.
So inside a black hole, does
Yeah.
time exist or not?
Inside the black hole, there is a singularity or not?
No. Inside a black hole, if there is a singularity also, so
Yeah.
inside the black hole, can we does the notion of time exist, or does the notion of time does not exist inside a black hole?
Okay. So, okay, that's another, of course, very good question. So, if you take the classical description of the black hole as in Einstein's theory, then of course the notion of time, inside the black hole is a little different. The normal time which the far away observer sees, that coordinate does not, remain as time-like. It's rather the radius that becomes. So it's something weird happens geometrically inside the horizon. Okay. So you don't even have to go to the singularity. Just inside the horizon, the time behaves in a somewhat funny way. As I said, the light flip and so on. But in this, we are just thinking of a black hole from outside only. Okay. So the modeling of the black hole here is that the outside of a black hole, okay, can be represented by the outside of a system of strings. Okay, one is not talking about here, the physics of the inside the horizon physics of the black hole. So that is complicated. In fact, that has remained complicated even now. How does one, describe the physics inside a black hole horizon from string theory or radius theory and these things? The work is still going on in these things, and this is an important question. In particular, the issue of the singularity. Okay, so let me therefore carry on. So what we therefore are showing here is that the black hole is a thermodynamic object. Okay, this is also said in this fashion that the black hole is a black hole. So black hole is intimately tied to this hot cup of tea. In fact, that gives this amazing correspondence between Einstein's equations and Navier-Stokes, the two very famous nonlinear equations of theoretical physics of the last couple of centuries. And in particular, this also says that the black hole arrow of time is the same as the thermodynamic arrow of time. Okay, so this therefore
Gautam, one more question which I think is quite good. So the question is that you mentioned Poincare recurrence theorem.
Yes.
That eventually the system will return to its initial state, even though the recurrence time might be huge. So the question is, does that mean that the arrow of time is only temporary in principle?
Absolutely.
Absolutely. Okay. And there is a second part. Or do things like the expansion of the universe and black holes prevent such recurrences?
So the point is whether so that's also a very good question. So black holes, if you describe them by classical gravity, then the arrow of time is absolute. Okay, things only go in. You can draw the Penrose diagram. You can draw the causal structure of the black hole space-time. Things go in, and absolutely no way that. Okay, it is only when we are talking going beyond the classical gravity description of black holes that we can say that okay, the black hole is essentially a thermodynamic object, and this arrow of time is approximate, and so on and so forth. So classically, it is correct that indeed it makes the arrow of time absolute. Okay, I think that was probably the spirit of the question. So okay, so let me just so this concludes for me the discussion of the two arrows of time. There is just one curiosity that I must make here. How do I understand the arrow of life in thermodynamic terms? Okay, So let's think of the origin of life. So life originated, as it is thought, from some hot primordial soup, okay, which is something like this. You know, it's some fluid, hot, and in equilibrium perhaps, and so on. It's some kind of hot soup. So this would be a very, very disordered system. Okay, but life is a very ordered object. You know, so it's like going from heads and tails equal proportions to all heads by itself. Okay, which is a very, very anti-thermodynamic arrow of time. It's an arrow of time, but it seems like the arrow of time in reverse, in which order comes up. Okay, of course, there's a lot of energy being fed into the system and so on and so forth. So one should not really expect that it should always go into it's an open system and so on. So there's a lot of story that one can say about this, but it's an interesting thing that order comes out of disorder, and a humongous amount of order comes out of disorder. So this arrow of life, of course, is unsolved. One does not know how exactly life arose from that hot primordial soup. The cosmological arrow of time is also unsolved. One doesn't quite know why the expanding universe is the only solution that we see. However, these are all difficult issues, and we'll discuss this some other time. For now, I end the talk, and thank you all.
Okay, Gautam, thanks for a very illuminating talk, and I think all the students especially enjoyed the talk very much. There are a few questions, and I'll take up those questions now.
Yes, please.
So, yeah. So, Anupam and Jaya Singh, you have I have unmuted you. Can you please unmute your mic and ask your question? Anupam and Jaya Singh, please ask your question. Okay. So I see another hand raised. This is A. Shiva Prasad. So Shiva, I have unmuted you. Please unmute your mic and ask your question. Shiva, please ask your question. Okay.
If you are unable to unmute yourself, then please write down the question in the chat box.
Hello, sir.
Yeah, we can hear you. Go on.
You told about the strings, like black holes has some sort of strings.
Yes.
Are they like open or closed? Like if they're open, then what kind of brains are there?
Okay, that's a very good question. So the first model where we showed this, computed the Hawking radiation, those were those two kinds of brains. Okay. D1 brains, which are string-like objects, and D5 brains, which are five-dimensional domain wall kind of objects in 10-dimensional space-time. And so they were actually wrapped in some five compact dimensions, leaving five non-compact dimensions. So these things were black holes in 5 dimensions. Okay, those were the calculations. Those were the models which were first used to compute the entropy of the black hole by Strominger and Waffa, and we computed the this model of excitation and de-excitation that I talked about. Let me go there. Yeah, this calculation that we did was with the D1.5 black hole, which described black holes in 5 dimensions. And in fact, here the degrees of freedom were indeed open strings which connected the D1 branes to the D5 branes. Does that answer the question?
Yes, sir. Sir, one more thing.
Yeah.
You told like it is some kind of 5-dimensional, right? So you told us about one particular length scale, that is the time length scale. Sorry, time scale. There has to be like other 4 scales as well, right? That confines this time reverse.
Yeah, unfortunately, I'm hearing a lot of echo. Can somebody else relay the question to me?
Can you please ask your question again once more?
Hello.
Bharat, can you ask your question again?
Sir, good evening, sir. Can you audible?
Yeah, hi. I mean, I can hear your
Sir, good
question,
evening,
but there's
sir. I'm
lots of
sorry for.
echoes. Yeah, say it. Ask
Sorry,
slowly
sir. This is
then.
a. Sir, sorry for the denies. I am traveling in the bus after completing my college, and I have only 2 questions. And why does why does time always seem to move forward and not backward? Could black holes give us a clue about reversing time?
Unfortunately, there's so much reverberation that I cannot
Sir,
hear very well. Rakesh, could you
sir,
hear
can
the
I type in
question?
the chat box?
So it's actually this question is related to your entire talk.
Yes, sir.
The question is why is there an arrow of time, and can black holes provide a hint towards this arrow of time?
Why there is an arrow of time and whether black holes can
Provide a
resolve?
hint towards the existence of this arrow of time.
Yeah, so this is basically what I try to show in these models of the molecules of ink spreading in the water, which I modeled by the shaking of coins. And basically, the reason why the arrow of time appears is that in certain kind of systems, the interactions are such that after some interactions, the memory of the initial state is forgotten. So the new state that it comes to is as if it's randomly chosen from all possible configurations. So in that situation, it's like a one random draw after another random draw. And it's very difficult to come back to this same original configuration, soon, because it keeps going through all kinds of possible configurations because the memory of the initial state is forgotten. Okay, this is what is the hallmark of a chaotic system, which also is described by the word ergodicity and so on. But on the other hand, as I said, not every system shows the arrow of time. Systems which do show the arrow of time, they can be described by an equilibrium thermodynamics and so on. But there are dynamical systems which are periodic, like the Earth-Moon system. so it just it's just periodic motion and it does not reach equilibrium. And what I showed for the black hole is that the black hole also has an arrow of time, which is an absolute arrow of time in classical gravity. But once you know that the black hole has a microscopic atomistic description, then the arrow of time does not remain absolute. It becomes approximate, and it is described by the same arrow of time as in thermodynamics, because the black hole has become a thermodynamic object. So that is it's a difficult thing, because before the work of Strominger and Bafa in 1996, nobody was able to find an atomistic model of a black hole. It required a theory which could describe black holes quantum mechanically, and that was possible for the first time in this particular context of the D-brane black holes string theory.
So we'll take a few more questions if it's all right, Gautam.
Yeah, sure.
Okay. So Dattatreya Mohanta, I have unmuted you. You had a question early on. So please unmute your mic and you can ask your question. Dattatreya. Just a minute. Yeah, go on. Okay, Dattatreya, if you want to type your question, that is fine. Then in the meantime, I'll take someone else. So Anupam and Jaya, your hands are still raised. So if you want to ask your question, please ask it now. I've unmuted you. Okay. Anupam Singh, you have a question, please ask.
Hello,
Anupam,
can you hear me?
Yeah, we can hear you.
Okay, great. So first, let me quickly, I'm a faculty member also at LNMIIT, so thank you for this wonderful talk. And the question is, if you have two different hypersurfaces in higher dimensional space, where the time is in different directions on the two different hypersurfaces, then in the bulk between them, do you have to have a singularity or a horizon is sufficient?
Yeah,
was the question clear?
Yeah. So you have the cusp in mind, is that right?
Well, actually, in general, I mean, I'm just thinking. Okay, I'll tell you the motivation since you asked.
Yes.
See, I mean, in Feynman's picture of antimatter having a different arrow of time, and matter having an arrow of time which is in a different direction. So if matter and antimatter were, let's say, isolated on two different hypersurfaces, and there was a bulk in between them, then would you have to have a singularity in between those two hypersurfaces, or horizon is sufficient?
Yeah, I mean, there would certainly be, okay, this is my guess, that there would certainly be a closed time-like curve, because this is something that happens across black hole horizons also. If you look at the causal diagram of a black hole, so there is a part of the manifold beyond the singularity also. Okay, especially if you have three-dimensional manifolds like this, what are called the BTC black holes. So the times do run in different directions, But using this, if you want to connect these two regions, then you can construct a closed time-like curve in which you can come back to your own past. And that is a causal singularity at least. I mean, whether it's a, necessarily a curvature singularity or not, it certainly is a causal singularity. So I think the answer to your question is that I would say that there is a causal singularity. If you want to connect regions with time arrows.
Great, thanks.
Thank you.
Okay, so I think we are reaching the end of our scheduled meeting. So let me just end by thanking Professor Gautam Mandal once again for a very fantastic talk and a very illuminating talk, which I hope all the students enjoyed very much. It certainly seems that way from the kind of questions they have been asking. So let's end today's.
Dattatreya has a question. So can you just take that question only?
Okay. Let me see.
Please unmute his microphone and.
Yeah, just give me a second. Yeah, Dattatreya, I have unmuted you. You can unmute your mic and ask the question.
Can you hear me?
Yes.
Yes.
Hello. Yeah. So
Yeah, hi.
my question is that I actually have two questions. The first one is that in the previous question, Gautam sir said that about the singularity to form to construction a time loop that takes us back to our past, that causal singularity. About that,
Yes.
my question is, so in the time river, if I want to come back, then the black hole is not a point that we can come back. So there has to be a white hole. So if there is a white hole, then how do you like to describe the Hawking's radiation?
Okay, so this is another important question. So, if you take this idealized black hole, which has existed forever, then, it is described by a black hole region, a white hole region. However, there are no white holes if a black hole is formed by gravitational collapse. So, because what happens is that that part of the Schwarzschild geometry, which would have been a white hole, is now actually covered by collapsing matter and is described by different metric. Typically, something like the Oppenheimer-Snyder metric inside. So as a result, there is no white hole in that situation. So of course, the collapsing black hole itself produces a boundary condition which is not time symmetric. But of course, this does not quite evade the arrow of time question. You could say that a black hole has been formed by a time irreversible process. So of course, it will violate the arrow of time. That's not the situation, because take a very late black hole, very old black hole, it has formed and so on and so forth. The history of the formation is forgotten. In that, it's almost static, nothing is happening. Then also, things can only go in and not come out. Therefore, you can ask the question of the arrow of time without going to the complication of the white hole.
Okay. And so, sir, I mean that time, is it that time doesn't exist inside a black hole? That is the thing.
I would say the following. If you look at the Oppenheimer-Snyder solution, it is like outside you have Schwarzschild black hole, which is static. Inside you have dynamics. Okay, namely that you have what is called it's like the contracting cosmology solution. okay, inside. So there is a time, no doubt. It is only the description of the time in terms of the outside Minkowski clock that is under question. But you certainly can use some clever coordinate system like the classical coordinates or Eddington-Finkelstein coordinate and so on and so forth, which does describe time very effectively inside the black hole horizon all the way up to gravity. So time certainly exists, but it is not the same time as what the asymptotically flat Minkowski observer will see.
Okay, sir. Thank you, sir.
Okay, so I see that there are several more questions, but unfortunately, we have run out of time. I mean, it's already 8 p.m. and we have to leave the speaker at some point in time. So very sorry if I'm not able to take up your questions, but maybe you'll have another opportunity to ask these questions on some other forum. So please forgive me that I'm not able to take up all the questions. And let us just thank Gautam once again for this wonderful colloquium. So that's all for tonight. Shubhayan, it's your call from here.
Yeah, sure.
Thank you.